Markus Sperling tell us more on magnetic quivers and subtractions. Please go ahead.
Thank you. Sorry. Put it next to your laptop. Sorry?
We need your word here.
Right. Yeah. So, right. Two things. So first, I'm not Simona. Unfortunately, there's going to be some reshuffling, so I'm going to talk about something else. Second, this is going to be, sort of continuing in spirit on the lectures Ami gave last week. But of course, I'm going to remind people that haven't been here last week on the things they may have missed. The third thing, if I speak too fast, not loud enough, or if I write unreadable, let me know. Otherwise, any questions anytime, and we're good to go. Right. So the idea is basically that if we have a symplectic singularity, right? So already good. The pattern of the workshop is covered. What we want that to be the Coulomb branch realization. So we want that to be the Coulomb branch of some magnetic Coulomb. Right. So that's good. And then what we want is to basically know for this singularity, for symplectic singularity, we know there's something that we call the Hus diagram, but it gives you this clarification. So if I may draw a picture, you may have something like this. Right? So we have this Hus diagram, which tells you something about the stratification. Into the symplectic leaf. So if you think about it, we can assign some basis to this. Let's say this is our symplectic singularity x, and then this is the next bigger leaf. Then we have here x2, then here we have sort of x3, and then if you want, we have the trivial one. And what Ami introduced last week, and what I'm going to review in a minute, is that starting from a magnetic quiver, there's the algorithm called Quivers subtraction. And Quivers subtraction basically produces you magnetic quivers, so Coulomb branch realization for these symplectic leaves. Right? So if we have Quivers subtraction, then what we get is we get for the xi, we know we have some Coulomb branch, which is the magnetic quiver qi. Right? That's all very, very nice. But then we see there's a bunch of other things which are sort of not immediately covered. Let me get some colors. Right.
Right, so you can ask, okay, so of course, the subtraction algorithm also tells you what is this kind of singularity, what is the minimum degeneration here. So here you get some, let's say some G, you get some A, whatever. Right, so what is covered is the leaves, and what is covered is the minimum degenerations. But you can also ask, what about the rest? So you can ask, what is this? What is this? No. All kinds of questions will be.
Sorry, just to clarify, what are the QIs here?
The MQI?
Yeah.
So MQ stands for magnetic quiver.
Yeah,
Yeah, I'm gonna review that in a second.
The different magnetic quiver.
Yes. So that's why you have an I here. So there's an index here. Sorry.
The X is a non-normal symplectic singularity or disconnected symplectic singularity or whatever.
You have your stratification, right, of X into the leaves. And then think about it, if you want to be strict, we get the closure of the leaf gives you, we have a Coulomb branch realization for that one.
I see.
Right, so the leaves are smooth, and then the closure is again isolated.
For every leaf closure, it's also a Coulomb branch.
Well, that's sort of the working assumption that we're working with. It's a symplectic singularity, and we are hopeful that we get a Coulomb branch realization for it. Right, so this is sort of the given or the sellout that we have from last week. And now the question is what are the other things? And you can ask also, what is it that put at more points? You can also ask more questions. But, right, so the sort of one thing is to answer what is these other things, and we want to find Coulomb branch realization. In terms of physics, there's also, kind of a natural question, because if you think about the Hasse diagram of telling you of the partial Higgs mechanism, and what you would usually start with is you have a theory T here at the bottom, and then you would do partial Higgs mechanism, right? You would do partial Higgs mechanism to a theory T1, to a theory T2, to
T3, and then to T4, which is trivial. Right? And then, if you look at it, the orange pieces here, they are precisely the Higgs branches of these theories. But the closed subtraction algorithm at the moment doesn't give you the magnetic probabilization of this theory immediately from the algorithm. Right? So by answering the question, how do we get this this non-minimal slice in a simple way, we also answer the question, how do we get the magnetic quiver that we get from oscillating from here to here? Is it clear what I'm wanting to do?
Yes.
If there's any questions.
When you say the orange arrow, what do you mean by that? I mean, do you mean a portion?
You want a slice from
The slice.
Slice up to the whole thing.
Right. So here's always the orange ones are always the slices from the top, right? And the Higgs bunches turn out to be the slices from the top. But if the diagram would be bigger, you could also consider like if there would be another point here, just, then you can also ask what is the slice between here and here, and then it's neither a leaf nor a slice to the top or bottom, right? And the answer basically, or the question is basically, can I find the Coulomb transpolations for all of these in a simple algorithmic way and not using some.
Are you going to say more about the partiality?
I might. Sure. Yeah, we can.
So like for the mathematicians to understand what is the question that it answers for physics.
Okay, sure.
The bit of an issue if you're doing between two different nodes, but are you really doing that, or is that not?
Say again the question?
There's a bit of an issue, I think, if you're talking about a red arrow between two different nodes, what is it that you consider important?
It is an intersection of the closure with the slice with a smaller one.
Yeah, that's just one way to define it.
Yeah,
but I don't think that that's always what the physicists mean.
It is always.
Well, because I mean,
It is always what?
not sure if that's always what the physicists mean.
But that's what he means here.
Yeah, that's what you mean.
Yeah.
Good. Any more questions? Good. Right. Now, we basically put some more material to this. And the starting point is that we go back to the brain systems that have been introduced last week. So we start by 3D and it was 4 brain systems. And just as a reminder, so we start in dimensions. I'm not going to use the colors because I don't remember. Right, so right here we have 3 objects that are going to be important. The principle they live in 10, but I'm only going to depict, the blackboard plane, so there's going to be some projection. But the end of the story is that this is a very nice way of constructing 3D and discrete theories and making their modular spaces sort of manifest in geometric drawing. So just to remind, we go to here, we have to here, and we have to here. And then we have various subspaces. This one is our spacetime. Right, so this is 2 + 1 dimensional. And here, let's see, here we sort of have, if we have, I cannot build it. So we have an SO 3, 3, 4, 5. And this is going to sit in SU to Coulomb. And to have blue, I have blue. And here I have an SO 3, 7, 8, 9, which is going to give us SU2. Just in brief, we have 3 94 theories. They have 2 types of barcode, Higgs and Coulomb branch, or Higgs and Coulomb barcode. The maximum branches are the Higgs and Coulomb branch. We know they are hyperkähler spaces, so there should be an SU2 rotating the complex structures. These are precisely these SU2s.
Do you mean infusion of groups, or is it the other way around?
What is an SO3 and that's the cover?
It's a question.
Sure. let's, okay, I'm just gonna put,
Just put an arrow.
sure.
You're looking at the way.
Yes.
No, the arrow, the
The
other
other way.
Very good. Very good. Right, and now, what I want to do is basically I want to remind you what things mean. So if I draw a picture, then here, when I draw these lines, I mean NS5, and then I have D3 in between. So I have a bunch of D3s. And then here we have the 6 direction, here we have the 3, 4, 5, and outside of my blackboard I have the 7, 8, 9. Right? So, what is now important is that we also can have the defilement. And now there's a, if you think about Higgs and Coulomb as being parameterized by some variables, then these variables, we can think of them as represented in the brane system by D3 branes moving between different types of pi branes. So that means if we have a D3 suspended between two NS pi branes, being able to move up and down in the direction, right? This direction that we can sort of visibly depict here is a Coulomb branch moduli. Right, so that tells you if I'm able to move a D3 brane between NS branes, then every single sort of degree of freedom that I can move gives me one quadratic dimension to my Coulomb branch. Happy with it? Not happy? Okay, sure. But let me know if there's a. Likewise, if I have so you know the defined branes they come out of my blackboard. So if I would have the D3 brane which is suspended between the D5 branes, which can now freely move outside my blackboard, oops, sorry, and this would be a Higgs branch modulus. Right. So now the whole nice point is that we can use this brane system to look at the 3D-4 gauge theory which is suitably realized. Then we can just look at how different branes are suspended between different pi branes, and then we can sort of at least count and also do some other things the vacuum moduli with. Right? So it's a nice way of seeing the way what kind of moduli are available and what we can open up. That's the whole point of it. You good with it? Very good. Okay. Good. Now, what I want to do is I want to basically focus on the question that I had here. So if I have a theory, I start from it, and now remember there's the electric and the magnetic one, and think about the electric one. Sorry?
No, you only start with the magnetic. Thinking about the electric.
Right, so, okay. So we have the electric. Right, so the electric theory is our T. And for this theory, we are interested in the Higgs branch. Right. And in order to answer that question, we want to find a magnetic quiver such that the Coulomb branch of this magnetic quiver gives us the corresponding Higgs branch. Very good. Now, what the brane system allows us is to construct the brane system for the electric theory, and then use the brane system to read of the magnetic quiver, which then describes as the Higgs branch. Of course, in 3 dimensions, you don't really need to do that, but for high dimensions, it's a very useful tool. So the starting point is that we want to understand the Higgs branch of the electric theory by using a Coulomb branch.
You're starting with a type A, you always have this magnetic quiver. If you're starting with some other quiver that you may not have.
If I start with a type A linear quiver, yes.
And you'll always have a magnetic quiver. But if you start with a non-type A, you may not have a magnetic quiver.
May happen, yes. Yes.
another comment is that in this quality it's not just the singular branch and Coulomb branch, but all symplectic resolutions or static resolution.
That's right. That's right.
We haven't talked about resolutions yet.
Yeah, but I'm making this point because there could be several theories with Coulomb branch, symplectic branch of the original theory, but in particular, from physics, we find one which also reproduces resolution.
Physics,
you find that the magnetic quiver is such that it reproduces not just a singular, not just a symplectic singularity, but also resolution.
Oh, I see. But the brain systems normally have them in a type A quiver, but for a general quiver, the brain system necessarily.
Maybe we can see what happens.
You know, I'm happy to discuss.
Okay.
Yeah, for generic quiver, we don't have a brain system, but for the ones we do have, we have a very nice picture. Right? So yeah, for the A-type one, you have the deformation, you have the resolution parameters, and on the magnetic quiver, basically they're just swapped.
I guess maybe I'm interrupting too much. It's just that if you're type A, I guess the whole picture is more or less clear. If your quiver is not type A, then I don't know whether you have brain system, I don't know whether you have that it's but you could specify which magnetic quiver is supposed to be the right one, then because of that.
But T might be not even T just something.
It doesn't have to even be
in our dimension.
You have only a magnetic quiver, and no electric quiver is electric.
Right. Right. So in many of the things, you can think about it, use the A-type example as guiding you, giving you some ideas, some insights, and then you just generalize the thing to other quivers. Right? So basically the same is here. We're gonna see some rules that work for linear A-type quivers. Now we're just gonna assume they work for any other quiver as well. And then we see where this goes. And it turns out actually it goes rather far. It gives consistent and verifiable results. And that's sort of the spirit of the way we take the things that we understand and just apply them to more general settings. Very good. More questions? Okay. What did I want to do? Yes. Right. Now we're going to do the Higgsing thing. Okay. So, Higgsing. So so let me, do we have an eraser? We do have an eraser. Okay. So Higgsing. So, and specifically, I want to do Higgs branch Higgsing. So what that means is the theory has different types of fields, different types of multiplets, and if they have a scalar component, we can give them a constant value, a vacuum expectation value. Right? And this vacuum expectation value is the one that sort of parameterizes the space of Buckle. And you can give different vacuum expectation values. You can give to some that live in the hypermultiplets, and that you give some to them that live in the vector multiplets. And depending on which you do, the resulting theories are going to be different ones. So let me illustrate that. If we have this theory, right? So here we have two D3 planes. So we're going to get a U2, and we have 4 flavor planes. Right? So what we can do, or what now means that we want to assign a vacuum expectation value to a multiplet that lives in or a hypermultiplet scalar, means that we want to suspend the D3 plane between D5 planes. Okay? Right, so we move one of them up. So we move the D3 plane up to the D5 planes, and then we can split the D3 plane along the D5 planes. Right? So since the D5 planes are coming out, like this, I can now move the pieces individually. Right? So I can move one here, I can move one here, and I can move one here. So you see that I get 3 moduli that I can choose. And what we think about this is that we give a vacuum expectation value to some of these hypermodules. So we give but now you give a vacuum expectation value to something that transforms non-trivially under the gauge group. So you need to check what is the residual or what is the commutant of that thing. So the random comes U1 with 2. Why is that? Because I can use the brain system to see what is always happening. So if I move this further, then I'm left with this. So I basically move the blue segments out of range, and then I'm still left with the D5 brains connected with one D3 brain to the NS brains. And then there's a rule that we had last week. We can move this one over here by annihilating the brain. Yes, that's the one. Very good, right? And then we see that here we only have one D3 brain left, and we have 2 flavors left, right? So that gives you the U1 with 2. That is sort of what we do when you assign a vacuum expectation value to a hypermotivated scalar. That means we suspend D3 brains between D5 brains, we move them away, and then we check what is the residual theory in the electric phase, which is D3 between NS5 brains. We can read them off, and then we see this is a partial Higgs mechanism. And now you might ask, why is it a partial Higgs mechanism? Well, because I can do more, right? There's still some D5 brains left, there's still some gauge symmetry left, so I can keep continuing, and then if I keep continuing, then I go to nothing. And that would just means I line this one, I break one out here, I move it away.
Well, I just so we're thinking of this as passing from human branch to some mixed branch for prostate, and then going off to like infinity or something, and mixed direction.
Yeah, that's the correct statement.
What the cool
right?
Something like that.
Yeah, it's correct. The starting point is you run the electric phase of the brain system, right? Because the D3 brains were between the NS5 brains. And then you sort of move them in a weird, well, not a weird, but in a mixed phase, where one D3 brain is in the electric, the other one is in the magnetic phase, right? And if you think about it just in terms of Higgsing, you just send them away, right? Very good. Now, very good. Thank you. So the next exercise that I want to do is, so I have a Higgs mechanism like this, and I basically want to know what is the effect on the magnetic quiver for this theory. Right. So for this, I'm just going to introduce 2 things. So we have some conserved quantities in the brain system. This is the number of NS brains, this is the number of D5 brains, and this is the linking numbers. And the linking numbers, you can just write down. So the linking numbers for the D5 is just the net number of D3 brains that end on them, minus the number of the other type of 5 brains on the left. So this is number of D3 on the left-hand side minus the number of D3 on the right-hand side, plus number of NS5 brains on the left-hand side. And if you do the same for the NS brain, then this part is the same, and we have plus the number of D5 on the left-hand side. So these are some numbers that need to be preserved in anything that I'm going to do to the brains. And why am I telling you this? is because there's sort of a nice relation of the linking number of the NS branes. So if I have two adjacent NS branes, then I know that the difference between them, gives me the balance, gives me the balance of the U and H node between them. Right, so last week we saw that there's a notion of balance. Right, so if I have this node, then the notion of balance is the number of flavors connected to it minus twice the rank. Right? It's drawing too much chalk. So here the balance would be 4 minus 2 times 2, so this would be 0, right? And we call this balance. And if it's positive, then it's overbalanced, which is also good. Sorry?
What is the sign?
Delta. Oh, well, yeah, maybe I shouldn't use delta. Excellent point, excellent point. Let's call it B for balance. Okay. Right. Now, why am I telling you this? I'm telling you this because there's the first transition that we want to look at. It is the A m-1 Higgs bunch transition. For this transition, what I want to look at m d5s with some linking numbers being the same. Well, they're constantly the same. Right, so I have m d5 branes which have the same linking number as a starting point. So what does it mean in terms of the brane system? Well, I know in the electric phase, there are no d3 branes suspended between d5 branes. Right, so I know the net number of this contribution is just 0. So I know that if they have all the same linking number, they all need to be in the same interval between NS branes. Right? So this tells you you have m d5s in the same intervals. Okay, and then the transition is the same as I showed you before. You just move one d3 brane up, you split it along the d5 branes, and you move them along the d5 direction. But then you know you have m d5 branes, so there are m-1 intervals between them. So we get m-1 Higgs bunch mode, which are given by the m-1 d3 segments. Okay, you happy with this?
I don't understand the linking.
So the linking number is just a quantity that's conserved for the moment.
What is left hand side?
What is left hand and right hand side?
Right, so you look at the brane.
Yes.
And it has a left and it has a right side.
And it's right.
Yeah. This is an NS brane.
Only those. So for
You define the linking numbers for the 5 branes. So for each type of 5 brane, you define a linking number.
what does suspend D and S mean?
This means for D5 and this means for NS5.
Can you explain it to these two?
Sure. Right, so if we look at this NS brane, right, so if you compute the linking number for this NS brane, then we look at the number of D3 branes coming from the, so from the left hand side, we see there's 0. On the right hand side, we see there's 2. Right, so I would compute the linking number to be 0 minus 2. And then do we see any NS branes on the left hand side? We don't see any, so there's 0 to 5. Sorry?
And then D5.
Yes, very good. Thank you. And then if we do the same exercise for the second one, we see we have 2 D3 branes on the left, 0 D3 branes on the right. Right, so we have 2 minus 0. And then we have 4 D5 branes on the left.
Yeah, maybe to clarify, number of D3 branes on the left-hand side means the number of D3
Oh, ending, yeah, ending.
on the 5 brane.
Yeah, sorry.
On the left.
Yes, so yeah, that's right. So you have them ending on the brane, right? So you see there's no D3 brane ending on the left, but there's 2 D3 branes ending on the right. Right, and you can see that the linking number here is the same, right? I mean, that's...
Sorry, the number of D5s, if you had a bigger brane system, you want all of the D5s on the left.
Yes.
Stop when you reach another minute.
No, everything to the left.
All of them.
Everything to the left. And right, and the, you know, the point appreciated in Amiens' paper in '96 is that if you do the transition, the linking number needs to be the same, and that's sort of why you need to do brane creation and annihilation. Because now, if you compute the same thing here, you should get the same numbers, right? Right. So if I compute the same thing here, then I see the number. Yeah, I'm getting 0. Very good. if I do the number of D3 branes ending on the left is 0, the number of D3 branes ending from the right is 1, so I have 0 minus 1. But then now, crucially, I have a D5 brane on the left-hand side. Right, so it's 0. And I can do the same exercise here.
It should be minus 1. Get the minus 2.
Sorry?
You want to get minus 2.
I want to get minus 2. Did I mess up the linking numbers? Let me check. That is very likely. Yes, I should take right minus left. My apologies. Very good. Very good. Right, sorry. Okay. Let's count the exercise again. Let me redo the exercise. So this should be 2, right? Let me see, why is it 2? We have 2 minus 0 minus 0. And then here, we have right minus left. So that's 0 minus 2 plus 4. So this is 2. Now, if I do the same exercise here, I have right minus left plus 1. So it's 0. And here,
Yes, 1 minus 0. You swap right or left. When you count this.
No, just in case down.
Again,
1 minus 1.
Right minus left is, no, down. This one.
here, right, okay. Right is 1. Yes, minus 0.
Plus 1.
Plus 1, very good. Amazing. And let me just do this here, just to convince everyone that I'm doing it right. So there's nothing here. There's minus 1 here, and there's plus 2, no, plus 3. Let me see.
No, plus 3.
Plus 3. Oh, yeah, very good. Very good.
Ah, yeah.
Very good. Right. Okay. So what's the point of this exercise? The point of the exercise is now that if I now allow myself for a moment to exchange NS branes and D5 branes for whatever reason. So if I do that, then after this exchange, I would see I have n NS5 with the same linking number, with identical LS I. And if I have identical link numbers for the NS branes, then I already know that the difference going to give me 0. So I'm going to find n minus 1 adjacent gauge nodes with balance being 0. Right. So maybe let's do an example for this. Let's do the same example. So what would be the magnetic field for this? Let me do this correctly. Should be the 1, 2, 1, 2 here. And now I see I do the Higgs bunch Higgsing here. But now what was the indication that we were looking for? We were looking for that this here, these were 4 d5 with same linking numbers. Now we see where they translate to. They translate to 4 and it's 5 with identical. Because all of them are balanced. Right? All of them are balanced because here, this one, for instance, has 2 flavors, minus twice the rank is 0. This one has 4 flavors, minus twice the rank. So all of them have balance 0. And now what is the corresponding Coulomb branch Higgsing? The Coulomb branch Higgsing now just becomes this.
So I didn't quite get the connection between your LS and
I start on the electric side. I start with MD5 branes that have identical linking numbers. And we concluded from this constraint in the electric phase of the brane system, meaning that the 3s are suspended only between NS branes. Then identical linking number translates to the d5 branes being between the same NS branes. Right? They cannot be scattered between different NS branes, they have to be in the same NS interval. Right? Then I allow myself, for what reason ever, to exchange d5 NS branes. Think of it as going through the magnetic thing. Right? Then this would mean I have m NS5 branes which have identical linking numbers. And then I told you here that the difference between linking numbers between adjacent NS branes translates to the balance of the corresponding gauge node between them.
Oh,
No worries. Right? And that's how I come up with m NS5 branes, same linking number translates to m minus 1 connected gauge nodes which have balance 0. Right? And this is just the example to show you that it translates to the same thing. And now, the thing that I want to get to is that you see, so here we sort of understand what is happening, right? This is sort of the thing that Amiens told you last week. You would do a 2, 4, you would subtract a 1, 2. Maybe should I do this one? Yeah, maybe I should.
That was what you had up there, the 4, 2, and the 1, 2.
I'm sorry?
All that you had up there, you're going back to that example, the 4, 2, twice the 1. Okay?
Yes. This is exactly this example. So I go 2, 4, or 4, 2. And then I do the Higgs bunch transition, right? So that is in the brane system, you have seen what this means. We go to 1, 2.
That's the partial Higgs.
That is correct. That is partial Higgs because this one is not trivial yet, right? But I still want to know what is the manifestation of this transition, this partial Higgsing, on the magnetic work, right? That is sort of the thing that I'm doing on this side, because this is the magnetic field for this theory. Now I do partial Higgsing. Now I want to know what is the corresponding magnetic field for this theory without computing it all the time, but just deriving it from this curve. Right? So for this, I just translated you because Higgs bunch Higgsing is driven by the flavor nodes, right? By the D5 branes. So the corresponding statement on the Coulomb bunch side should be driven by the NS branes or by the topological symmetry, which is the notion of the balance.
But in this picture, sorry,
Yes.
the 4, 2 is the quiver 4, 2 is what we call the electric quiver.
Yes.
Even though what you're drawing is
Electric, just think about, the Coulomb branch phase of the brain system, and it's the ninth phase that allows me to draw this quiver quickly. Right? Because Coulomb branch phase tells me I can identify immediately the gauge group, so I can tell you what is the node. And then, since the defibrils are not connected to anything, they're just sitting there, I can just tell you where the box is. Right? And the electric now just means that I'm just interested in the Higgs bond of this thing. Right?
But the picture, the configuration are the Coulomb.
Yeah, it's drawn in the electric phase, so you have the Coulomb branch moduli. Right, so if you want, right, so if I draw you this, right, so now all of the D3 bins are on top of each other. So now, really honestly, here I have a UN. If I draw you this, then here the UN would be broken to the torus. Right, so here you would have some U1 to the N. So this is sort of, you're moving out on the Coulomb branch.
Is this something you're getting from partial Higgs, you think?
Which one now?
What is this of UN, the U1 to the N?
Yeah, you give a vacuum excitation rate to the W bosons. So there's some Cartan elements and there's some how do you call them, ladder operators? You think of them as ladder operators, like the one that build up the UN representation, and basically those have become massive. So they're not contributing to the massive spectrum anymore. Sure. So what's the confusion? Just
well, I got confused because you were talking about Coulomb branch of a magnetic quiver.
Yes.
The electric field.
Yes.
But now the quiver that we're writing down, you're calling the electric quiver.
Right. So this one is the electric quiver. I want to know the Higgs bunch of that thing.
Yes, you want to know the Higgs bunch of this. We haven't written down the quiver that we're taking Coulomb branch of.
Right. The quivers that we take in Coulomb branches are those ones. Right. So in this theory, I'm interested in the Higgs bunch. Higgs bunch physically means that we're basically probing what are the partial Higgs mechanisms. Right? Because you can think of sitting at the origin of your modular space, and then you're sort of probing some minimal directions which are the singular ones, and those are triggering the partial Higgs mechanism. Right? So this is basically the physical meaning of this picture, right? So if I draw this picture for over here, right, so this is my Higgs bunch Hasse diagram. And now, in terms of the electric theory, sorry, this is the small. So this is the electric theory. So I start at the bottom with the electric theory. And when I tell you this, I mean there's no Higgs bunch moduli turned on. Now I start tuning on some Higgs bunch moduli in a minimal fashion. Then I go to this point. I get a 1, 2. Right? Then I can ask what Higgs bunch moduli can I turn on here? I can turn on another one because that's sort of the picture here. Right? I can move this up here. I can choose one Higgs bunch modulus. But then after this, I have no electric theory left. I mean, it's trivial. Right? So, in this sense, this one becomes now the Higgs bunch of this T, and this one becomes the Higgs bunch of this T1. Right? And if you want, this one is the Higgs bunch of trivial. Very good. Now, we have a magnetic quiver that gives us this Higgs bunch, which is this one. If you do Quivers subtraction, then you will get the magnetic quiver for this one. But now what I want to do here is I want to get the magnetic quiver for this one straight from the diagram. In this example, it's, you don't really have to go through all the hassle of doing it, but for other magnetic quivers, which are more general, it's a nice algorithm to work it out. Right? So we look at an A3 here and we look at an A1 here. Right? And now the point that I wanted to advocate, is if they have the Higgs branch AM-1 transition, the corresponding effect on the Coulomb branch, or on the magnetic quiver, so the corresponding effect on the magnetic quiver is we subtract the finite AM-1 Dayton diagram from the balance nodes. Because this is more or less what we're doing here, right? We have a balance set, so we subtract the A3 finite Dayton diagram, and we're going to end up with this quiver, which is the magnetic quiver for this thing.
Expect that you're supposed to subtract an A3 because you computed A3.
Well, why subtract the A3?
Yeah,
Right, so I know what is the corresponding, I know what is happening if I do the Higgs branch transition here, right? So I move a bunch of D3 bands out along the D5. If I go to the corresponding magnetic side, I know now what I need to do is I need to have n-1 segments moving between the NS branes. n-1 segments moving between the NS branes is precisely moving away one Coulomb branch modulus of n-1 adjacent gauge nodes to the Coulomb. That is precisely what I'm doing here. I'm moving one Coulomb branch modulus C, one Coulomb branch modulus C, one Coulomb branch modulus C, and move them away. I've reduced the rank by 1. That is, morally speaking, subtracting the finite A3 data.
why you, in general, there's some rule that you were going to tell us that you subtract something. When you do partial Higgs, it's always subtracting A.
Yes. Now that if I get to it, there are two sets of rules. There's one set of rules for the things that Amiens has been talking or introducing last week. That is going to be based on subtracting fine Dayton diagrams. There's the other set of rules, which we're going to work out here, is subtracting finite Dayton diagrams. And basically what you do is if you subtract the fine ones, you go from the top to the bottom. If you subtract the finite ones, you go the other way. That is precisely what we want, because here, right? So here, the subtraction algorithm that we have, is you subtract in this way. So we have a quiver, you assume that you have a list of all possible slices, which are usually fine Dayton diagrams and some other stuff. You subtract them, and then you get the next magnetic quiver giving you another lead. But now we want to go the other way up. Right? And the other way up is now going to be subtracting finite Dayton diagrams, plus other stuff. Right? So it's just a different algorithm that goes from a different direction, and then you can really nail down any possible slice in the puzzle area.
I don't know if it helps, but maybe you can explain what you're subtracting in the electric theory just by looking at the brain diagram.
Yes. So here, very good. Right. So the thing we said last week is important. Right, so what was the important concept last week that Arno told us? If you see something like this, a 2 with a 4, then let me maybe make some space. Can I erase this one here? Good. Right, so what is the... So last week we said something like this. We had 2 4. And then what we would subtract is we would look at this 4, and we would subtract a 1 4. Right? We would subtract a 1 4, And then we would, what would we get? We would get a 1 and a 2. Very good. Let's do a bigger example and mention the important point. If I would have something like this, and I would do a hex function transition here, I would do the same thing. I would subtract now with 2 and a 1 here. Right? Then I would do the subtraction here. I would get a 1, 1, 1. But now, in hex function hexing, the balance needs to be preserved. Why is that? Because I'm just doing stuff along the default branes, and the linking numbers are preserved, so the NS branes, they still need to have the same linking numbers as before. Right? They still need to have the same linking numbers, means the balance application is the same as before.
Why was it subtracting 4 1 against 4?
Why is subtracting 4 1?
Because it was taking a V3 brain on top to intersect
Right.
or V5 brain.
Yeah, this is literally moving the 1v3 up, and then we have the corresponding or participating flavor brains.
And you rebalance that.
Right, and I need to rebalance because the linking numbers of the NS brains are preserved, so the balance is preserved in the process of hex function hexing. That's why I need to rebalance. Right? And rebalance then tells you you need to put a 1.
So you really only need to subtract the engagement, not rebalance. You need to subtract the framing nodes as well.
That's what we do in the
Right, so in this one, the top down, I need to rebalance. In every step, I need to rebalance. In the other one, I don't need to rebalance. I just subtract the final thing, but I'm sort of restricted to the set of balance nodes plus other things. Right, so that's the difference. Okay.
What if they have or flavor or in the framing node was related to that. So the fact you wanted just to subtract at the gauge node, but then you would forget that there are 4 flavors, and that's what tells you that the transition is shape 3.
Right. If you know what the balance is against negatives and
I'm just saying that the structure of the figure that you subtract tells you about the transit.
right, I guess so. But if you're going to rebalance that, then you can effectively code all the framing just using the balance.
You are not going to hold the information of the thing relationship. What you are saying is that if you subtract 1 4, is going to be the same as if you subtract 1 and 3.
Right.
But the 4 is important because the 4 tells you that the slice is set.
Oh, I see. You want to have that part of the equation.
Yeah, move on. There's some algorithm that we don't understand 100%, but I think
Okay.
I don't want to derail and talk anymore than has already happened. So,
So basically what I want to do in the last 20 minutes is just go through an example, do the 2 algorithms side by side, and show you what we get. Does it sound good? Cool. Okay. And I'm going to move, erase this one. Right. So for the moment, there's only 2 things that we need to know. So there's, let's call it standard Quivers subtraction. And then let's call it the inverted. And I only need 2 rules for each. So if I want to have the AM minus 1 transition, let's say the AM transition, then here I subtract morally this one. So this one is the affine AN, plus I need to rebalance. So that's rule number one. And then if I have the climbing one, then what I need to do is I need to have this one with B plus 2 in between plus rebalance. Right, two rules for the eight things. In the inverted subtraction, how they translate to is you just subtract this one. Finite AN. You just subtract finite AN and nothing else. No rebalancing either.
You should say that it's balanced.
Sure. Okay. Okay, maybe I write this better.
You can.
So from subquiver, we subtract right, so on one side here, you don't need to care about the balance of the thing, you just need to care about the shape, but then you need to rebalance. Here you need to care about the balance, but then after this you don't. And the last one is from page node with balance B. From balance B, you subtract just a 1. Right? Again, you need to check a segregation node. You need to evaluate its balance, and then you subtract a -1 on that node. Modulo sum.
Okay, B. Okay.
And assuming the code at the end is good. Are you happy with the two rules? No.
Well, so there are two cases.
It's just the first.
Yeah, then it's sort of the same.
Sure.
It's a general case.
This
Okay, let me now just check the example so I'm not telling you some nonsense. Where's the example? Here. Very good. So for this example, the electric theory I'm looking at is this one. 2, 3, 1, 4. Right? And we know the corresponding magnetic quiver is what? Is this one. 1, 3, 2, 1. Okay. Now I want to compute the Higgs transfer diagram for this thing in two ways, starting from the magnetic quiver. Good. And if I give names to it, just go with it. Right. So here we start from the standard thing. That means we do precisely what we were instructed. We look at this thing. And then we see that it's in the realm of this rule because we can write this right. We can write it like this. And then I see here I'm precisely in this rule. Right, so first transition gives me an A3. We'll go with this? No?
So should there be a gauge node at the top?
I mean, so it's firstly, the top of the record site.
Yes.
So this be a square, so this be a negation or triangle. Does that make a big difference? Is it a box? Is it a square or is it?
So in principle, there's a U1 that is sort of acting free, so you can just remove that one. If I right. So if I remove this one, I'm going to go back to this one.
Okay, no, it's fine, it's fine.
Right.
It's more about the thing I don't understand.
Right. Good. Both ways are fine. The way you like it, both ways fine. You can use this. You can look at the 4. You just do the same thing here as we had last week, and then you subtract an A2. If you do this, you're going to end up with a quiver that looks like 2, 2, 2, 2. And if you want to write it in the same fashion as here, then I write it like this. Right. Now I see that I have 2 options. I can do either way. I can either give a web here, I can give a web here, or I do this transition or this transition. Right, so I get an A1 here and I get an A1 here. And the corresponding codes are just like mirror to each other. So one of them would be 1, 2, 3, and this would be the other one. Sorry. Happy with it? And if you want, we can write it like this. Am I doing this right? Yeah. Sorry. I'm doing the wrong thing. Sorry, I started with the wrong program. Forget what I said the last 5 minutes. I looked at the wrong quiver, sorry. We can also do that one. Yeah. Sorry. And then this one we write as so here, same thing, we look at this one and we get an A2. And here we end up with this one. Which we write as it's a bit more interesting because now we have the 2 rules popping up. So this one was the same rule as here we have this Kleinian singularity. Here now we have 2 choices because we have 2 versions of the affine A2 inside that diagram. And again, we can subtract the 2 choices. Right, so here we get an A2 and we get an A2. What do we get? If you do it on the left-hand side, we're going to get 1, a 2, a 1, and a 2. If you do it on the right-hand side, we're going to get 1, 1, 1, 1. And we're going to get a 2 here, and we're going to get a 1 here, which is the same as writing it like this. And this one I can write equivalently as right. The 2 quivers are different, but in both of them I see I can do another Kleinian singularity following this rule. That they meet now is not, but you need to do the computation, then you see that both subtractions give you the same code. Right, so if I subtract this here, I'm going to get, so I get the 1 by 1, I need to rebalance, so I will get this. And if I do the same exercise here, I will subtract the 1, 2 here, this one's gone, and then I need to rebalance this one, so I get the same code. Which again, I write as right. And then the last thing is now we just subtract the A3.
And now, all the magnetic quivers that we have computed, they give us the magnetic quivers for the leaves. Right? So this is the magnetic quiver from here to here. This is the magnetic quiver from here to here. So now this one from here to here, and this one from here to here. Right? Okay, now we do the same exercise, just the other way around. Are you happy with this? Also happy?
So you have to get rid of all of the, you have to convert it to something with no framing that is subtract the affine, then put framings back.
You don't have to. So you can either work this on this side, or you can already work on this side. Both fine. It is this one sort of nice is nicer if you go to magnetic quivers for like higher theories, because then there's no framing anyway. So this one is sort of the natural way of subtracting. But for 3D, perfectly fine to do this. Right here, you can subtract a 1 with box 3. You get to this, and you rebalance.
But on the right, you subtracted a 1, 1, a 1 connected to a 1, like 3. You come there to there, you subtracted the 1, 1.
Here, I subtracted the declinium.
If you want to apply the rules here, you have to do it at the end.
Yeah,
The 1, 1, right? The 1 connected by 3 arrows to 1.
So the unframed version of this one is and the unframed version of this is this.
I mean, frame.
Yeah, the framed version.
But I'm happy working on the unframed side, but I'm just saying you subtracted a 1 connected to a 1 from the unframed side. Right?
I subtracted this one.
Yeah, 1 connected to a 1. So you got 1, 2, 2, 1 above. Yes, but you put a 1 back there, is what I'm saying. So you didn't really subtract off the 1.
It's the rebalancing of
That's what I was thinking, you have to rebalance.
Yes, it
You said on the
is.
unframed side you don't have to rebalance.
So this is unframed rebalancing, so you add the 1 and you add edges.
Yes.
on that one.
Yes. So think of this as the rebalance node.
I thought that you said that if you do the unframed version, you don't have to rebalance.
No.
No, it's in inversion.
So this side, right? Too many things. So this side is this standard thing. The standard thing. In the standard thing, you look at your quiver, you look at the subset of graphs you find, and you look whether let's say unframed, right? Unframed. You look at whether there's an affine or whether there's a line and a singularity hidden in there. You just look at it, you just look at the structure. The nodes don't need to be balanced or anything, they just need to be there. I subtract it, but after subtraction I need to rebalance, so I need to preserve the balance. Right? This is the thing that we have done here.
Yeah.
And this node is basically precisely this, right? So this is the rebalance, so you put them all together, you're back to the 1. Right. In the next thing that we're going to do on the other side, in the next 5 minutes, we look at the quiver. And we do care about the balance of the gauge nodes. We look at the quiver, we look at the balance set, and then we decide what we can do. And we don't need to rebalance. And we're going to do the other way up. So now, I'm going to start here. Framed, unframed.
It's okay.
Okay.
Either way.
Okay.
One says unframed.
Very good. Right, and now just for convenience, I'm gonna color out things that are not balanced. Probably some not balanced. Right? So I have this quiver, it's the same as there. For some reason I start at the bottom, and now I look at this quiver, and I see what is balanced. Balance is this piece. Right? So now following the thing that I wrote on the other slide, on the other board, is this will tell me that I can now subtract an A3 finite Lincoln diagram.
Subtract as much as possible, I guess.
Sorry?
You're required to subtract as much as possible.
Yeah, you always need to take the maximum choice.
Because then, so if you wouldn't do it, so this operation decreases the balance of the adjacent nodes, right? So if you would do that, and the node is already balanced here, then you would be bad, and you need to subtract the maximum connected balance. Find nothing like that. Very good. So let's do this. So here, let me just frame this here. This is a finite. Sorry, this is a 1, and this is a 0, right? So this is a 0, so I'm going to stop writing that. Right, so I'm going to end up with this one. Now I do the same game. I look at a set of balanced nodes, and I see this one is not balanced because there are too many, and this one is also not balanced. Right? So now I see I have two balanced nodes, but they're not connected to each other. So I can do one I can choose. I could do this one, so this is a A1, or I could do this one. Right, so I'm gonna go here and I'm gonna go there. So allow me to do the right on the right hand side. So I'm gonna get a 1, 2, and then this one is not balanced. And here I get the other thing, so just the reflection. And then again, I look at the nodes to the balanced set of nodes. So I get an A2 here, and I get an A2 here. Again, you need to compute that they meet, but they meet. And what are we left with? We are left with this one. And then this one. Both of them are unbalanced. Right, so we have no balanced nodes left. So the only thing that we can do is now this one. Right, so we need to compute the balance of this node. And what do we compute it to is 3 minus 1. 3 minus 2 is 1 plus 1 should be A2. Is that correct? Yeah. Now, why don't they have 2 of them? Why don't I have 2 of them? Because I work framed. Yeah, that's only one choice. Right, but now, so what's the difference? The difference is now that the Quivers that we computed, now they basically compute me slices from the top. Right, so this is the magnetic quiver from here to here, but this one now is the magnetic quiver from here to here. Right, so this one is the magnetic quiver for the partial Higgsing from here to here. Similarly here, what is this? This magnetic quiver here is the one for this slice. Okay, and now in the next 2 minutes, you can do a silly thing, right? I mean, you have one way to go from bottom and one way from go to top, so you can ask, what is the magnetic quiver from here to here? Is it easy to see? Right, so you can ask, what is the thing in between, like any random point in between? Right, so what is now the nice part of it? Well, it's very easy to construct, because I know that inverted subtraction precisely gives me a magnetic quiver that measures this slice to the top. Right, so the first step is we take the magnetic quiver for this one, which is this one. Now, in the second step, I want to get rid of the top. But I know how to get rid of the top, because that's basically just the standard code subtraction from the top. So what I need to do is I need to subtract the A2, right? And subtracting the A2 is now subtracting this piece here. So here, I'm going to end up with a 1, 2, am I doing this right? Like this, right? Does it work? Like this. What would you think? Okay. Right. Very good. And right, so we see also this quiver doesn't show up anywhere in any of these subtractions, right? So it's really the combination of both to compute this non-minimal size. Right. So long story short, is the code subtraction that I'm introduced goes from top to bottom. So we compute the magnetic quivers for the symplectic leads and the certification. Now with the other way up, we can first of all compute the slices from the top. So these are the Higgs, these are the magnetic quivers for the theory after partial Higgs. But most importantly, we can now combine both of them and compute anything in between by just following the simple recipe of subtracting either finite or fine organic items plus some extra conditions. So that's sort of the logic of it. We moderated this on the brain system in the 3D setup, where you can just derive it and you don't really need to do all of these things. But then you can sort of propose that the same rules apply to any magnetic field that you encounter, and then you can see that it will do. That's sort of the experiment. Very good. Then, first of all, thank you very much for giving me more time, and if there's any more questions.
How do we know the weighting between subtractions or allowed flows?
Sorry?
How do we know the weighting between subtractions? Such as the one on the right, right, or straight arrow, yeah, are allowed flows?
This is a composition.
I don't know what I'm speaking. It's just the composition of the, say, the slide like that. That's it.
Well, think of it as a Higgs mechanism, right? It's like, so at the bottom I have this theory, and under the first partial Higgsing I have this theory, and then this one has Higgsings which go in this way.
Or you ask a slightly different question. Along which direction is the free energy increasing?
Don't know.
Any of these are allowed flows? Different flows?
Should be. I don't.
Both directions?
Say again, what's the question?
Both directions allowed.
So Higgsing goes this way, right?
What's the picture on the left?
This is normal quiver subtraction.
So, or Higgsing on this way?
Higgsing is always this way.
They come differently. They come differently. Like the ASCII diagram is not sorted by its branch dimension, but the complementary.
That's exactly.
So the, right,
Where is the flow?
the full theory is here, the trivial one is here.
Okay.
Because
Quivers capture the transverse slides.
right here I have this one. This is the electric theory that I'm looking at. So this one sits here. Right, so this one sits here. Then I do a partial Higgs mechanism of this theory, and then I'm going to be here. And here I'm going to be left with nothing.
You're flowing down this way.
I'm flowing up.
Yeah, but can you call it down?
Sure, yeah, but this way up. You're good with that?
All this actually.
Sure.
So I didn't quite get how you got the rules for inverted quiver subtraction. Maybe
That was a beautiful derivation. Go ahead, yeah.
do they follow from observation of linking number?
Yeah.
Do you have the other linking number?
Sorry?
Do you have the linking number as opposed to the one you used before?
The proper linking numbers. Let's say you have the well-defined linking numbers. You can look at the Higgs branch transition, right? So you have the link numbers for the d5 branes. You do mirror symmetry. You get the linking numbers for the NS branes. and then you know what is happening. It's basically the same picture, but now everything moves along the NS branes. But then you know, since the link numbers are the same, you know that there's a balanced set of nodes. And then you just postulate this as the rule for subtracting the balanced set. And then you can do the same thing with like a detailed thinking quiver. It's sort of the same thing. If you start with the electric theory, which is SP, you write it in terms of branes, you look at the link numbers, then on the mirror you get a detailed thinking quiver, and you see what you can subtract for the finite or for the Higgs-Matrix transition. Is the finite
I guess
thinking.
my question is how the best approach should I think of it having some extra node, some bigger node, and then
No.
rebalance?
No. It is literally just subtracting the finite thinking diagram. It is the same as if you look at the zero sigma theories, right? So one partition gives you the motion on the D5, one gives you the NS5 ring. If you do the Higgs-Matrix transition, you're only changing the partition for the D5 ring, the NS ones untouched. If you do the quarter-bunch Higgs, you move the partition for the NS rings. And if you just compare the Quivers, that's precisely what you do. You just subtract the finite thinking diagram for the balanced subset.
So should I think of this quiver that subtracting as the one that I'm drawing on that describes the Coulomb branch?
Yes. Precisely. Right? So
that's why the Coulomb branch of this is moved. Okay.
Right, let's say let's thank Marcus again.
Really brief comment. So that, I mean, I don't quite know my old book, but the left-hand side is basically slicing it, right? The rules very precisely correspond to what we call the Malcolm born of those transitions in the Amiens planning. The thing on the right-hand side is generalized slice, right? Is this what you think of it as? Okay, well, it can be thought of as generalized slice. It's going the other way around. So this is basically the negative weights corresponding to the negative co-weights corresponding to positive co-weights. So I think there's a way of understanding this in a very sort of pure mathematical, with no reference to technical parameters. I think you can understand this purely combinatorial in terms of
In the case of a frame, yes, but this is much more general.
okay, yeah.
I'll say this. Let's thank Marcus the third time.